Hello, I'm Chang.
And I'm Rachel Gehlhar. And today we are presenting on recurrent neural network control of a hybrid dynamic transfemoral prosthesis with EdgeDRNN Accelerator. To start, I will talk about why we are studying powered prostheses in general. On the right, you can see this powered prosthesis called AMPRO3 in my lab at Caltech. This is designed for someone with an above-the-knee amputation. There are currently over 200,000 Americans with this type of amputation. However, they are limited by the current devices that are energetically passive. Amputees expend about 33% more energy in walking than healthy humans with these devices. These devices also require heuristic hand tuning for every patient, which is very time-consuming. The advantage of powered prostheses is that they are powered by a battery and can move on their own, so they provide net power to the user. They are also capable of more dynamic behaviors, such as stair climbing. Finally, we can design these control methods to improve safety and comfortability for the user. Most powered prostheses are controlled by impedance control, which requires a lot of hand tuning. However, our lab developed a trajectory tracking method that does not require as much hand tuning. The limitations of this current prosthesis control method, though, is that complex controllers are computationally expensive to calculate online. Also, the human nonlinear dynamics affect prosthesis dynamics and are difficult to model, so this limits the type of controllers that we can use. To address these limitations, we investigated using recurrent neural networks, which Chang will now talk about.
So our solution is to train an RNN controller running on a hardware accelerator, which is called EdgeDRNN. There are two reasons we want to use RNNs. The first one is that RNNs can imitate complex controllers with scarce training data. And the second one is that RNNs have potential to be retrained on personal data to model human dynamics without hand tuning. Although RNNs are computationally intensive, EdgeDRNN Accelerator exploits spike-based temporal sparsity, which improves energy efficiency by up to a factor of 50 times. Moreover, it enables computing large multi-layer RNNs at a total power budget of only 2 watts.
I will now describe the current prosthesis control method of a PD controller. To develop trajectories for the prosthesis, we model the entire human prosthesis system as a 5-link bipedal system. Every time the foot hits the ground in walking, this impact causes a discrete jump in velocities. Hence, we model the system as a hybrid system where there are continuous phases for when the leg is standing and swinging and discrete dynamics to model the impacts. With this model, we design periodic output trajectories offline for the prosthesis that account for these impacts. You can see an example here of a periodic orbit, and this straight portion is for the discrete jump. The curved portion models the continuous phases. After designing these trajectories, we develop a PD controller to determine the torque based on the positional and velocity error, as well as just a couple tune gains. This control law aims to reduce the error between the actual trajectory and the desired trajectory so that this error goes to 0. You can see in this flow diagram that the prosthesis knee and ankle joint positions are measured, and based on this, we determine where in the desired trajectory we want to be. Now, based on the error between the desired trajectory and the actual trajectory, we calculate the PD controller. This determines the torque to send to each of the motors. This is the basic control scheme for the prosthesis, and now Chang will talk about the RNN and how this is integrated into our control method.
So as for the RNN controller, our method is to use imitation learning for the RNN to mimic PD. As shown in this diagram, we simply replace the PD knee controller and the PD ankle controller with a single RNN controller network, which is trained using the error of the position and the velocity of motors to generate torques to control the knee and ankle of the AMPRO. So in this project, there are two main challenges. The first one is that we need low latency for real-time control, and the second one is that we need low power required for portability. So both challenges are addressed by using the EdgeDRNN Accelerator. Next, I want to talk about the step-by-step implementation of this work. First, we have to collect process data in walking experiments. Next, we train an RNN on collect data. Then we run the RNN on EdgeDRNN in real time. Finally, RNN outputs are sent to the prosthesis BeagleBone Black microcontroller by SPI to control the motors. The picture shows how the EdgeDRNN board is physically connected to the BeagleBone board through the SPI interface. Both of the boards are lightweighted and can be attached to the prosthesis. Now I want to talk about the key results of this work, which including offline and online evaluation. To do the offline evaluation, we collect 3 datasets. The first one is the train set, which has around 210 seconds data. And we also have depth set and test set, both of them having 70 seconds of data. We train a RNN, which has 2 layers, and each layer has 128 neurons. And here are the results. Both of the plots show the torque outputs of the PD controller and the RNN controller over time for both the knee and the ankle. The red dots are RNN outputs, and the black are PD outputs, which are the ground truths. So as you can see, red overlaps black well, indicates that RNN closely models PD controller behavior. For the online evaluation, we compare the tracking performance of PD controllers and the RNN controller on different slopes. As you can see from the plots, the black curve is the flat ground training dataset, which is identical in all 3 plots. The red curves are the RNN controller outputs. Slope walking introduced disturbance in ankle motion and human dynamics. RNN still tracked knee trajectories well, showing it generalized well. To conclude, this work is the first instance of imitation learning for prosthesis control. It is also the first realization of an end-to-end RNN control of a robotic prosthesis functioning with human in the real world. It's also the first work to use a hardware-accelerated RNN for real-time control.
Now, while this work did not improve upon the prosthesis PD controller, that was not the goal. It did provide a proof of concept of an RNN working on hardware fast enough to be included in real-time control. This opens the door to potential future applications, such as building simpler models of complex controllers for efficient computing, modeling the human dynamics to capture nonlinearities and complexities of human behavior to include in prosthesis control, such that we can develop an RNN model-based control. Finally, by learning the individual human gait behavior, we can account for human intent in prosthesis control, such as predicting when the human wants to start and stop and speed up and slow down. Here's a video of our final result, where on the top you can see the prosthesis being controlled by the PD controller, and on the bottom you see the prosthesis controlled by the RNN controller. I am the one walking here in the video, and I could not tell a difference between the 2 controllers. You can also not see a difference in the video. And just to remind you, the RNN was trained only on flat ground data, but it worked well for both walking up and down slopes as well. Finally, we'd like to thank Dr. Shih-Chii Liu and Dr. Tobi Delbruck from ETH, as well as Dr. Aaron Ames from Caltech. We'd also like to thank Andrew Taylor and Dr. Yi-Sung Yu from Caltech, who advised on this paper. Finally, we'd like to thank the Telluride Neuromorphic Workshop, where this work started. Without this workshop, our work would not be possible. We really enjoyed being part of this workshop and the opportunity to collaborate. Thank you.